Okay, that seems to have slowed down. I haven't seen anyone jump on in the last minute or so. So we will get started. Good morning. My name is Nicole Parsons. I am a project manager and technical lead in building facade design. And I'm going to be talking to you today about fenestrations, or for, to keep it a little simpler, windows specifically. Fenestrations can also include doors and skylights, but we're going to focus on windows today to kind of start it off. We're going to start with some basic information. My understanding is that everyone here is from different kinds of education and experience backgrounds. So some of you may be familiar with windows and how they're constructed, how they're chosen, the impact that they have on building durability and energy use. And some of you, this may be all brand new. So I've tried to take it back to basics, but we'll also have that 15-minute question period afterwards. So if there's anything that that anyone wants to get explained in a little bit more detail, we can definitely do that then. We're going to talk about the components of both windows and curtain wall. We're going to talk about some basic terminology that we're going to be using throughout the presentation, the definitions of those. We're going to look at the role of windows in building durability, as well as the impact on the building's energy use. And that is going to then lead us to talking about the amount of windows in a building, the window to wall ratio, talking about window systems, so a little bit more in-depth look at the various components of the window and how each of those plays a role in the window's overall performance. And then we're going to briefly take a look at window installation and perimeter considerations, because it's fantastic to have a wonderful window, but if it doesn't get put in the building properly, then what's the point? So we're going to look at the cross section of a window, and sorry, I'm just turning on my drawing feature so that I can, there we go, my arrow feature, so that I can point stuff out as needed. So this is the cross section of a fairly basic window. This could be similar to a window that is in your house, that's in a low-rise multi-unit residential house, potentially high rises as well, depending on the exact configuration. But so we have the frame here at the bottom. In this case, this is an aluminum, a metal frame, because it's separated here by a thermal break. If it was a vinyl frame, for example, in a house, it would look very similar, but it wouldn't have this separation. It would all be made of vinyl. We have the IGU, which is the insulating glass unit, the glass in your window. This one has 2 panes. Sometimes they have more. We'll talk about that in a little while as well. And then the pieces that hold the glass in and that provide a seal to prevent the water from getting in. So we're going to talk about specifically the frame, the material of the frame. We're going to talk about the IGU. We're going to talk about the glass, as well as coatings that can be put on the glass, which is annotated here by the dotted red line. And then we're going to talk about this component here, which is called the spacer, which is what both provides space between the glass as well as what holds the pieces of glass together. It's a critical structural element of your IGU, but it's also a important thing to consider when we're talking about thermal performance of the entire system as well. Sorry, for some reason, no, this is going to let me. There we go. So we'll also look at curtain wall. Curtain wall is more used in large commercial buildings, high rises, buildings in downtown Toronto. It can also be used as storefronts in strip malls or anything like that, where you see those very large, floor to ceiling windows when you're entering a store from the street level. That's framing that can be very similar to curtain wall framing. And so this is kind of a breakout of what that looks like. So we have, sorry, I keep losing my my arrow here. So we have this section here, which is the back framing of the curtain wall. And so anyone that's ever, been in university buildings that have curtain wall, office buildings, anything like that, you'll probably have seen this. Lots of times, this is where the interior drywall is, if this was not a window. So you'll see some of this framing. And then, like the regular windows, we have the IGUs. And all the same components. The IGUs are all the same considerations, so we'll get into that. In aluminum systems, again, we have a thermal break, which separates basically the metal on the inside from the metal on the outside to help improve the energy performance of the system to prevent that kind of heat transfer. And you'll see in the annotation, I've said aluminum systems only because we're going to talk about fiberglass curtain wall as well. And then we have, as we're working out, we have gaskets. These are meant to help control water and air leakage. We have a pressure plate, which is screwed in through into the frame. So the glass is sandwiched between the interior frame portion and this outside plate that gets screwed on with gaskets so that it's sandwiched in place there. And then we have cover caps that just get snapped on the outside. Those are mostly for aesthetics, as well as there will be drainage holes in the pressure plates to allow water to move through the system. And the cover caps help cover those so we don't get all kinds of things deciding to make their homes in these small spaces. So we're going to go over some different definitions, some of which I have maybe mentioned a little bit already, but they're going to be important because I'm going to be referring back to them as I work through the presentation today. So thermal resistance is a heat property. It's the measurement of the temperature difference by which a material or object resists a heat flow. So essentially, the higher the thermal resistance, the better insulator a material is. The better it resists heat flow. The thermal transmittance is the reciprocal of that. That's the U value, and that's the rate of transfer of heat through matter, through a specific item. So for windows, we're going to be talking about U value. So the lower the U value, the less heat transfer that happens through that window assembly. Material conductivity, I have alluded to briefly about the aluminum and fiberglass curtain wall sections. So the conductivity is the measure of its ability to conduct heat. And apparently now my it's going to go ahead easily. So aluminum conducts heat very easily. That's why we have a thermal break of a polymer material to help separate the inside and outside aluminum to minimize that heat transfer. Whereas fiberglass has a much lower conductivity, so it doesn't transfer nearly as much heat, and we don't have a thermal break because fiberglass is already quite good on its own at that performance. Then we have solar heat gain coefficient, and That's the fraction of solar radiation that's admitted through a window, door, or skylight. That's going to be important because that looks at the glass, the IGUs in the assemblies, and that is mostly impacted by the coatings that we're going to talk about that you can put on the glass. And although more heat coming through the glass in the winter to help heat up the space seems like a good thing to reduce energy, there are comfort issues and things to consider that we'll get into in a little bit more detail. Then we have the visible light transmittance, which again is related to the IGUs. That's the fraction of the visible spectrum of sunlight, weighted based on the sensitivity of the human eye, that is transmitted through the window, door, or skylight. So it's a bit of a balance, right? You don't want to make a window have too low of a visible light transmittance in order to try to get a good solar heat gain, because what's the point of having a window if you're not getting those good that good natural light into a space? So it's a bit of a balance, and we'll talk about that a little bit as well. And then a thermal bridge is the movement of heat across an object that is more conductive than the materials around it. So when we get near the end, when we're talking about window perimeter detailing, we'll be talking about thermal bridging, because if we put all this effort into having these amazing frames that really reduce heat transfer, and then we put them in the building and we introduce a thermal bridge all the way around the perimeter, we're really negating a lot of that effort. So we'll talk about that very briefly as well. So if we're going to, we'll jump into considerations for durability. One of the things about building better buildings is obviously we want to look at the energy performance, but we also want to talk about the durability of that building. We want that building to last a very long time. We want it to be functional and serve its purpose, so that we minimize waste in the long term. So when we're talking about windows and durability, we're talking about moisture safety. We don't want water issues. We're talking about air leakage. We don't want excess air leaking. For the window assemblies themselves, thankfully, air leakage requirements are very well defined in the building code and in the then referenced CSA standards. So air leakage really becomes a consideration of the perimeters of those windows and how they're installed in the building. The thermal performance of those windows, we've talked a bit about some of those terminologies and some of those components. We'll get into that in a bit more detail. And then the last one that isn't always considered is occupant comfort. If a building doesn't make the occupants comfortable, that's something that can really push a building into premature replacement of components and premature materials landing in the landfill that if they had been better selected, they could still be in use. So we're going to include occupant comfort as one of the features that we keep coming back to as we work through the various components. So the first thing, if we talk about energy use and heating and cooling loads, these are some graphs from a study that was done that looked at the impact of different architectural features of a building on the heating and cooling load. So this looked at mostly buildings, I believe, that were modeled, some that were existing, and it looked at what size of an impact did these different things have. So you can see that of the architectural features, so this is, mechanical systems are not included in this. Electrical systems are not included in this. This is just the architectural features of a building. The building envelope is over half of both the heating and cooling loads. So then we broke down envelope parameters a little bit farther to look at what specific elements is that. So you're going to be hearing about opaque walls a little bit later today with Alex this afternoon, I believe. But for now, we're going to talk about windows. So for heating loads, the two window performance parameters that can help reduce, or if not properly selected, increase building heating loads are the window thermal performance, as well as the window to wall ratio. And those have about equal impacts on heating loads. And then when we move down to cooling loads, we see that the windows have almost 100% of the impact of the envelope on cooling loads. The opaque wall and window thermal performance is a very small slice. And so we're looking at the window to wall ratio, how much windows there are. And then we're looking at the window performance from a solar heat gain perspective. So again, I had mentioned that is how much of the heat from the sun can transfer through the window. So obviously, if a lot of that sun heat is transferring through the window in the summertime, that's going to significantly increase the amount of cooling demand in that space. So that's an important consideration there. So if we move into window to wall ratio being the first element of that we're going to talk about before we get into the specific window construction itself. So this has impacts on heating and cooling and occupant comfort. You can't have a window to wall ratio that's too low, or else you're going to feel like you're in a basement. But also a window to wall ratio that's too high, if there's not proper solar control, can also impact occupant comfort. This is a graph that looks at how window to wall ratio coupled with the window thermal performance and the wall, so the opaque area thermal performance, impacts the overall building thermal performance. So it's a lot. I've highlighted just a couple specific places to show you. So this red line is I don't want to say typical, it is probably the higher end of what is currently normal construction, quote unquote normal construction. There are buildings that are being built that perform better, but those are buildings that are specifically targeting being high performance. There are buildings still being built that are worse. So if we look at the red line and think that this is, good construction, at a window to wall ratio of 20, which is quite low, we get an overall thermal resistance of the assembly at R7.5. If we then go to 100% window to wall ratio, which means there are condos that are pretty much 100% window to wall ratio, the overall performance is then R2.5. So you can see it's 1/3 of the performance if you're at 20%. If you're at 40% window to wall ratio, which is a pretty good midpoint, it's a pretty good balance, that works out to be about R5. So you can see that these are not percent, these are not like decimal changes. These are actual impactful changes just by adjusting the window to wall ratio, even from 20 to 40. And what kind of the impact that those have on the energy modeling, I think will probably be talked about a little bit more tomorrow. So I'm not going to get into that. That's a little bit in depth for today. So I've included some illustrations that just give you a feeling for what different window to wall ratios look like. So we've got 25, 50, and 75. The thing to consider with the 75 is that there's still noticeable breaks between those windows, whereas we have some building, some condos in Toronto where it's pretty much all glass. If we go to the next slide, so I've pulled a couple photos. This is a condo conversion in downtown Toronto. The original building was built in 1883 in the top left there. And you can see that there are a nice few windows, but there's also a lot of wall area. I've been in this building. I've worked on this building. None of the spaces feel dark. There's lots of natural light. And then on the right, top right, we have a building that was started construction in 2018, also in Toronto, so a new build condo. And you can see that in this building, there's been a lot of effort made to provide adequate windows, but also to make sure that they keep that window to wall ratio at a reasonable level so that we get good energy performance of the enclosures. At the bottom here, we have an example of what we had for too many years in between those two. And this is an example of where even in front of the columns, it's all glass. People are, that panoramic view is gorgeous, but there's really nothing you can do to improve the thermal performance of that building, beyond the very low level of what the range of performances can be. And thankfully, the City of Toronto is, with their green standard, is taking steps to drive people towards that more reasonable window to wall balance. So we move on from window to wall ratio to actually get into talking about windows themselves, now that we know their windows are critically important, but we don't want too many of them. So this is a very basic schematic of what we're going to be talking about. So we're going to talk about the frame material. We're going to talk about that spacer material between the panes of glass and the IGU. We're going to talk about the number of pieces of glass in the IGU. We're going to talk about the glazing emissivity. Sorry, we're not going to talk about the glazing emissivity. We're going to talk about the coatings. So instead of emissivity, we're going to talk about the winter tide, but we're not going to get into that much detail. We're going to talk about the coatings on the glass and how they impact things like solar heat gain and visible light transmittance. And the glass between the panes, I don't have anything in detail on that. So we're just going to talk about that briefly before we go on. Typical IGUs have argon gas between the frames or between the glass. 90% or higher of argon gas, so that's actually pumped in while the regular air is forced out, and that improves the insulating value of those glass units. That is fairly pretty much industry standard. It's very rare to see windows these days without it, and it is currently the best balance between cost and performance. You can use krypton or xenon, but then you get into issues where you're not getting as much kind of additional benefit compared to the additional cost from going from argon. And some of those better insulating, those other gases they perform better in much smaller spaces. So then you're getting into situations where your glass panes are very close together. And it's something that gets looked at sometimes in extremely high performing buildings, but typically we're looking at argon between the panes of glass. So just to look at how the window U value can impact the overall thermal performance of a building, I brought this chart back. And so if we're looking, what I've done is if you look at the purple, green, and yellow lines, those all represent the same wall R value of R20. And I've drawn that red line down vertically that represents the 40% window to wall ratio. And you can see that the window values are 0.15, 0.25, and 0.35 for the U values. And the overall building R value changes from R6 to 7.5 to 11 when you look, and that's everything else is the same, just the windows are changing. So going from a fairly low performing window to, or I would say an average, 0.35 is probably average, a little bit better than average, to a very high performing window at that 0.15, that you can almost double the effective R value of the building. Now, a 0.15 window is a very high performing window. There's obviously costs associated with that, but it is possible for the windows to have a significant impact on the building's overall performance. So we'll dive into a little bit more about the different components of the window and how those can help kind of get you towards those higher performing windows for thermal performance. We'll also talk a little bit about occupant comfort as we go through. So we're looking at the basic frame materials for windows are wood, vinyl, fiberglass, and aluminum. So we're presented with these options, and then we have to decide. And in order to make those decisions, we have to look at combustibility. In low rise, you can use combustible materials like wood or vinyl. As you move into mid and high rise, there are a lot more limitations on that. Material durability against weathering. Wood windows are nice in a house. They are used less and less now because of the maintenance. A lot of people use vinyl because they don't have to paint it every year or every 2 years. You have to look at the structural loading. How tall is the building? What kind of wind loads are you expecting? Are these windows close to the floor? Do they need to provide a guard performance to prevent somebody from falling out? All of those things. The thermal performance, of course, which is the crux of what we're talking about. Configurations and glass size limitations. Different frame materials are going to have different limitations as to how far the members can span. If you want really tall glass, that's going to limit your choices. And then cost and availability, of course, because there are systems that exist to build incredibly high performance buildings, but many of them are expensive, and many of them have availability considerations if they are new, and there's maybe only a couple companies that make them, and so it becomes a balancing act. So we're going to talk about fiberglass and aluminum as we move through. When we're talking about anything that is not a low-rise building, basically, or anything that's not low-rise residential, pretty much, possibly mid-rise residential, we're talking about fiberglass and aluminum, really. So any kind of commercial buildings, any institutional buildings like universities and hospitals and all of that kind of stuff, we're talking about fiberglass or aluminum. So this is a therm model. Some of you may have seen therm models before, some of you may not have. So I am going to give you a little bit of background on it so that you can better understand. Essentially, it's a computer model that models a specific configuration of a component, and the outside is wintertime. So in this case, the purple is the outside, and the purple in our climate would represent typically -18. And then the inside, the darkest color on the inside, which is the red, represents +20, +21, depending on what the design conditions are for inside the space. So you can see that so this is a thermally broken aluminum frame, similar to what we looked at the beginning. You can see that the frame itself never gets to be red. The frame itself is green, which is kind of part the way in between that -20 and +20, just to keep it easy, we'll say +20. And so even with this thermal break, there's a nice bit of heat loss through this aluminum frame. And then we look at the fiberglass frame, and you can see that the inside surface of that fiberglass frame is red or orange or yellow in a couple places. Right here at the spacer, it's green, and we're going to talk about how the spacer impacts thermal performance in a few minutes. So you can see that the inside temperature of this frame stays a lot warmer. There's a lot less heat loss through a fiberglass frame. That also, a cold frame, anybody that's ever sat beside a window in the winter knows that even if you're not touching that cold frame, you can tell that it's cold, right? It impacts your comfort sitting very close to that window. So, it would be great if we could just build everything with fiberglass frames. They're more expensive. There's not as many options on the market. There can be, it can be a longer supply time. There are combustibility concerns. There are fiberglass frames that are test it to all of the fire standards for the building code, but not all of them are. So there are a lot of these considerations that that sometimes keep us away from using them. But you can see from this that they do, from a thermal perspective, they do perform better. So then, only got about 25 minutes left, so I might have to speed up a little bit. So then we talk about the frames, we go to the insulating glass units, thermal performance, solar heat gain, and occupant comfort impacts. So when we're talking about the glass, the few things that we've hit on already. So you have that heat gain through the glass. You have a certain amount of solar heat that's transmitted through the glass, which is that top orange arrow. And then you have a certain amount of heat that's reflected back to the outside that's not allowed to pass through the glass. The low E coatings that you choose for the glass will impact that. Same with the visible light that's transmitted, that yellow arrow in the middle. Our goal is, in most situations, our goal is to have a lot of that visible light transmitted through, because we want people to have the benefits of natural light. We want to reduce the need for electrical lighting in the space. But a little bit of it is always going to be reflected back to the outside. And then that red arrow near the bottom is the heat loss through the insulating glass unit. So that's based on the U value of the glass. And that's where that argon in the gap, which is pointed out by that second arrow up from the bottom, that's where that argon comes in and helping improve the insulating value of the unit. It helps reduce the amount of heat loss that is happening through the glass unit itself. Then we have the spacers. When we looked at that therm image of the aluminum and the fiberglass frames, I pointed out that in that fiberglass frame, right at that IGU spacer was really the coldest point inside on the window assembly. So this is how that is assembled. This is a cross section through an IGU. You have the glass on either side. You have the glass on either side, and then you have this spacer. In this case, this is a metal spacer. It's filled with a desiccant, which is kind of like those little packs that you get, when you get new shoes, and they have those little packs that say "do not eat." Those are desiccants. They just absorb any small amounts of moisture that may be in the air to keep the space that they're in dry. So any incidental moisture that is between the panes of glass, the desiccant will absorb that so that you don't get fogging inside your units. When units fog, it means that the seal is failed. There's too much moisture getting in, the desiccant can't keep up. Then you have sealant on the sides of the spacer to adhere it to the glass, hold it all together, and you have your seal at the bottom that provides that continuous seal to keep your argon inside and your outside air outside. And then we'll look at, I said we were going to look at different numbers of pieces of glass. So this is our standard double glaze that we've seen in all of these images that I've shown you so far. Triple glazed is becoming more popular. Triple glazed gives you two added benefits. One, you get an extra airspace that you fill with argon and an extra piece of glass. So that improves the U value of the assembly, the heat that, this is backwards, but this arrow is backwards, but the heat that would escape through the glass unit is reduced because you have this extra insulating airspace with argon and an extra piece of glass. It also gives you the benefit of being able to apply additional coatings. So the blue here is a low emissivity coating, and I mean, there are so many on the market that we don't have time to even get into that, into the specifics, but basically they're coatings that control the solar heat gain and that ideally still let a lot of visible light in. So, and it may be a little bit, I guess there maybe I want to just clarify, these are solar control low E's that we're talking about here. These are specifically coatings that are designed to reject the heat from the sun. There are other coatings which are more passive low E coatings, which allow significantly more heat from the sun to pass through. While that can be beneficial to the heating loads in the winter, it's problematic in two senses. One, we're getting a lot hotter summers here, so it would be detrimental to the cooling loads in the summer. Even though we are still a heating dominated climate, we do need to take that into account. And then the second thing is the comfort of the users in the space. So an anecdotal kind of story. I worked in Calgary for a couple of years, and our building had passive, more of a passive low E coating on the windows. And even when it was minus 40 outside in the winter, the sun in Calgary is very low in the winter, very low in the sky. So you're getting like a direct sunlight onto the building. You couldn't sit within 4 or 5 feet at least of the windows, because even though it was minus 40 outside and the enclosure was not great on the building, there was a lot of heat loss through the walls and the windows. The solar gains through those windows were enough to heat up that first 4 or 5 feet so much that it was uncomfortable to sit there. So it's really, that's just a little kind of anecdote about how it's about more than energy. It's about balancing all those things. And we really need to make sure that we're not sacrificing comfort, making a space way too hot in the interest of saving energy. So if we get into the spacers a little bit, these are some profiles of different spacers. So we have, at the top, we have metal spacers. These are pretty standard, pretty basic. They used to be made from aluminum. You will still run into aluminum sometimes now. Unfortunately, aluminum has a very high conductivity. It is the worst to use from an energy performance standpoint and maintaining or controlling heat loss. Stainless steel is less conductive than aluminum, and we do still run into these stainless steel spacers, and there are situations where they are perfectly adequate and suitable for the situation. Then we move, however, the more typical approach currently is to use what they're calling the improved metal spacer. So these are spacers that don't have metal all the way around. So you can see in that first one in the row that it's open. So here, so there is still, this is still a thermal bridge between the two pieces of glass, but it's not a complete. And this is a very similar situation where they have like a plastic top on it. So aesthetically, it looks a little bit nicer, but it performs the same. You can also get hybrid ones where you have metal and then you have maybe plastic all the way around inside. We also can get into composite foam and thermoplastic spacers, which are non-metal spacers. Some of them have a metallized film on them. They are significantly higher performance in terms of the thermal performance. They significantly reduce the heat loss through that spacer. But there are other considerations in terms of long-term track records, durability, and certain things like that. So they have their place, but their place is not everywhere. It has to be the right situation to use those kinds of spacers. So here in the top left, we have an illustration basically of heat, as an arrow moving through an aluminum spacer versus a foam spacer. A lot moves through in the aluminum, very little moves through in the foam spacer, kind of what we were just talking about. The top right shows cross-section through actual glass units with 3 different kinds of spacers. So the one on the right is a full metal spacer. The one in the middle is that kind of U-shaped metal with that plastic top on it. And then the one on the left is the foam spacer. And then across the bottom, we have some images. So in terms of occupant comfort, another thing to consider is that temperature, even in a very high performing fiberglass frame, that temperature at the edge there, we want to try to control it because we want to minimize the situations where we have a cold enough temperature to form condensation. This is an illustration that just shows, in the same conditions, extreme cold conditions, but in the same conditions, a full metal spacer, you're going to have significant condensation. Less metal, it reduces. And then if you're able to go with a non-metallic spacer, you can pretty much eliminate that with the proper frame and glass selections. So just that kind of quick comparison between them, all of these things to consider when trying to balance everything together. So if we look at perimeter conditions briefly, we'll talk about a couple things. So this is on the right is a thermal image taken with an infrared camera. And it illustrates, if you look on the left, you think, okay, well, there's a window and there's a concrete block wall and looks pretty normal, like you'd see inside maybe like an elementary school or a secondary school. And I don't actually know where this picture was taken, but that's the kind of construction that you would typically see inside an elementary school or a secondary school, right? You have those concrete block walls, you have this window. On the right is an image taken with an infrared camera, like I said. And for lack of a better description, you have the wispy color changes. So while they're interpreting infrared images is just that interpretation, you can't say this is definitively something. But these kind of wispy patterns here suggest that you have air leaking around the perimeter of that window. So you have this window, it's been tested to be airtight based on the building code and on all of those very well-defined requirements, and you have air leaking around the perimeter of the window. So something that we definitely want to avoid, and we'll talk a little bit about a few ways to do that and things to consider. So these sections are curtain wall sections, just for comparison. The wall sections beside the curtain wall are very poor thermal performance. You can see that they have insulation inside the stud space. They have nothing outside. Insulation here inside the stud space, but there's nothing here outside behind the brick cladding. Alex will talk more about why that is not a great way to build a wall that you're trying to get in it if you're trying to get an energy efficient building. I'll talk about more about that this afternoon. But essentially, the reason that I've pulled these up is to show the need for that seal. So it's very common, there's a seal inside. It helps make it look nice if the framing is exposed. There's a seal on the outside. It helps keep bulk water from getting into the system. This seal here at the line of, depending on the type of framing you're using, at that air water control line, basically in the framing, can be missed. So as a minimum, you should absolutely have sealant around to connect the opaque wall to the window. Ideally, in most situations, you would use a more durable solution, which is the image on the right, which is a little bit pixelated. I apologize. Here they use some kind of a flexible membrane. There are a bunch of different flexible membranes available on the market to do that, but it it's adhered to the wall air control layer, and it's adhered to the frame. And then it's also, because it's within, I'll use this one because it's a little bit clearer, because it's within this space and there's this component that that fills the space, it essentially gets clamped into place. So it's held there. It can't, fall out or get dislodged because it's mechanically clamped in place as well. So it's a much more durable solution to air control around the perimeter of windows. And then, of course, you still have that outside air sealant and the inside sealant that are pretty typical. Those are the inside and outside ones are not the ones that get missed. It's this hidden seal that's back in the wall that tends to get missed. And then, so let's then very briefly, because we don't have a lot of time, talk about window perimeter thermal performance. So we talked about thermal bridging a little bit at the beginning. And so these are, again, therm models of window assemblies. And if we look at, go back one, if we look at this, you can see that you have this, sorry, let me turn my, let me turn my arrow on again. You have this space that runs between the frame and the wall. And there's nothing in that space other than some foam backer rods and some sealant, or some foam backer rods and some membrane. None of which really provide very good thermal performance, right? So you're in a situation where you have this wall, which ideally is not built like this. And Alex will talk about how that wall should be built. So you have this wall that is hopefully fantastic. And you have this window assembly that is hopefully fantastic. And you put them together and you end up with this, 3/4 inch or inch space between them that is not fantastic. So you, and part of that issue is that there has been allowances in the building code in Ontario to ignore some of these things for a very long time. They've been trying to slowly roll out energy requirements and increase the requirements, and get the industry on board. So people have been allowed to ignore that in their energy modeling for their buildings, which is problematic, of course, because your building is not going to ignore it. You're not just going to not lose heat because you didn't model it, right? Thankfully, the City of Toronto Green Standard requires you take those things into account. You have to look at the losses around things like window perimeters, door perimeters, transitions between different assemblies, all of that kind of stuff. So the Toronto Green Standard is requiring that. Hopefully the building code will require it sooner rather than later, and it's something that more effort will be put into addressing how to minimize the losses at those locations. So on that note, again, as I said, these are therm models. This one on the left is similar to the images we were just looking at, except in this case, they have insulation on the outside instead of inside of the wall, which is better. And you can see that in this case, the framing is green. There's a lot of green. There's a lot of green that comes back into the cavity space here, and that's from bridging at the perimeter. There's likely some kind of an angle or something that's holding the window in place, and also just the fact that there's a break in the insulation between the window frame and the wall. So you have this space where your heat loss is significantly more, and also then as a result you end up with colder temperatures on the inside, raising risks of condensation colder frames, making people not as comfortable if they have to sit close to the windows, all of that kind of good stuff, or not good stuff. And then if you move over to this image on the right, this is what they're calling an integrated system. So what this illustrates is a window assembly that is integrated into the exterior wall insulation. So you don't have that gap. You end up with two assemblies that marry together to provide that continuity of thermal resistance. This is not something that is standard in the industry yet. These are from a metal sandwich panel manufacturer, which is the kind of panels you typically see in cold rooms or on warehouses, that kind of stuff. But it is something that people are beginning to think about. So you can see that in this case where they have integrated them to avoid that 3/4 inch space of nothingness, that, yeah, there is a little bit of a space where the heat loss is higher, where the surface temperature has dropped a little bit here. You've got your stud, you've got the framing, everything lines up. But in general, those interior surfaces are staying significantly warmer. There's no green anywhere on the interior surfaces, and that indicates a reduction in heat loss, as well as that improved comfort. So that's more of a thing to consider for the future, but things that we need to be considering. That brings me to the end of my presentation. We've got a couple minutes before we'll move over to the question session. Thank you. I look forward to your questions in the next section, and your code for this presentation is 2 + 2 = window.
All right, thank you so much for the wonderful presentation. Just a reminder for everyone, the Q&A is in a separate session, so if you could head back to Feedloop, that would be great. Sorry? And Nicole will see you there.
Yes, right. Thank you.
Then I'll just end the session early unless anyone has a quick question to drop in. The chat's open. Okay. Yes. Okay. So someone does have a question.
Sure.
Milad says, hi, thank you for your great presentation. I have a quick question here. What are the possible errors during the construction phase?
So for Windows specifically, there's a few different possible errors. The most basic one is installation of the glass backwards. So if I go back to this slide, you can see that these coatings are on, if you have a 2-pane piece of glass, the coating is on the inside surface of the outside piece of glass. There have been, right here, I have seen it happen where the glass gets installed backwards, and now that coating ends up being on this surface of the inside piece of glass, and that fundamentally changes its performance. It doesn't perform as well, or it performs differently. So you're not getting the performance that you're looking for if you want it on that number 2 surface. If it ends up on the number 3 surface, it's different performance. And there, depending on the coating and the situation, it can also cause a durability concern, because there can be a lot of heat reflected back into this airspace in the glass unit, which can cause premature failure of the seals. And then the other big thing with windows, because windows are pre-manufactured in a factory, there's a lot more quality control. The big issue is that perimeter detailing when you're on site and you're installing those windows. I would say that it's relatively rare that it gets missed entirely, but it's fairly common and a fairly easy thing to do if you there's a corner missed. You're having to overlap materials, and they don't seal together properly. So that detailing to making sure you have that continuous seal to prevent that air leakage around the perimeter is also really important, and it is something that can be missed on site.
Thank you very much. That follows up with some sort of errors that make the windows perform in a way that we do not expect, and also how would we consider them in our energy modeling?
So it's difficult to consider them in the energy modeling because they're not things that you can necessarily quantify ahead of time. However, the air leakage targets, so the backwards glass is something that would end up getting, if there's proper quality control, that's going to end up getting fixed. That's not something that would typically stay that way. And if only a couple pieces of glass are put in backwards, you can visibly see the difference from the outside. So that's something that typically gets addressed. So it ends up not being something you have to reflect in your energy modeling. Things like incomplete seals around the perimeters, increasing air leakage. Those are things that we are still struggling as an industry with in terms of reflecting that in energy modeling. There are some allowances within the standard kind of air leakage rates that are used for the enclosure within energy modeling. There are some allowances for some air movement. We're not modeling things at 100% airtight. But then in order to verify that that's been met, you end up needing to do air tightness testing of the actual building. Again, which is something that is becoming more common in the industry. It is something that Toronto Green Standard is introducing, but it's still new. It's not commonplace. So that's definitely I don't want to say a shortfall, but that's definitely a potential weak point when you're talking about modeling assumptions versus actual performance. So really the way to do that is to verify that. And the assumptions are made based on testing of existing buildings, right? A lot of the air tightness that's used in modeling is based on what built buildings do. So verifying that the building has actually been built to that standard is really the important part.
All right. Thank you, everyone, for your questions. Thank you, Nicole, for your presentation. The meeting is over now. Please head back to Feedloop.